So let's start lecture 3.4. This is more conceptual and visual than anything else. So we're pretty much looking at polynomial functions, but we're extending the degree of the polynomial function, and we're dividing the degree into even and odd. So this first table right here, this is f of x is equal to x, and that's clearly a polynomial function. And that's x is the same as x raised to the first power, and 1 is odd. So all three of these depictions right here, these graphs, are of odd degree function. Notice the difference in the endpoint behavior. We'll talk more about that later. This is a degree 1 polynomial function. It's the identity function, and it goes straight through the origin at a 45-degree angle. Again, we don't discuss angles in algebra. That's a geometric notion, but most of you know what a 45-degree angle is here. Here we have x cubed, which is the next odd degree function, moving up in size of oddness. And again, notice, instead of the end points on this is the positive side of the x-axis, this is the negative side of the x-axis. Here notice it shoots off toward infinity and shoots off toward negative infinity. The same happens here. It just does so steeper. In other words, by the time you hit x is equal to 2, f of x is already equal to 2 cubed, which is 8. Over here, when you hit 2, f of x is also equal to 2 because it's the identity function. And again, f of x is equal to x to the 5th. It rises to the right and falls down to the left, as is stated here, but at a greater pace, a greater clip. Let's actually explore a few of these functions. This is y is equal to x. Y is equal to x cubed. Y is equal to x to the 5th. No, I didn't type it in. Y is equal to x to the 5th. There we go. And let's kind of zoom in here. So this is y is equal to x cubed, and y is equal to x to the 5th. So kind of notice the differences here. It's flatter, but then rises steeper and overtakes it. Let's do one more. Y is equal to x to the 7th. And I'm perfectly fine if you do this. This is geogebra.org. Geogebra.org. I don't know if you can see that or not. You can email me if you can't read it. It's a good place to just graph. Let's do one more. Y is equal to x to the 1001 degree. Wow. Look at that. It's almost a square. Comes up. We zoom in really close. You can see it's not quite a right angle there, but it's quite a departure from the curviness that we see here. But our degree is an odd degree. It's 1001, and that's the extreme behavior of such a high degree. So down here, let's go back, and in all of our previous examples, our leading coefficient was 1. So let's go back and look at these examples. I'll turn off the x to the 1001 degree, and let's change the leading coefficient slightly. So this is y is equal to x. So you should know if I make it 2x, the slope is steeper because y is equal to mx, that's the slope. And if I were to choose, instead of 2, 1/3, then our slope is more shallow. Here, with our y is equal to x cubed, let's do 5x cubed. See the difference? Now let's do 1/5 x cubed. We're expecting it to be wider. Now let's make that negative. And it flips the direction. So that's going to be a general theme about the sign of the leading coefficient. And we'll talk more about that later. So those were our odd degree. So notice that the endpoints of odd degree functions rise to the right or fall to the left, or, as we'll see later, they might rise to the left and fall to the right. But when we look at even degree functions, they either stay completely above the x-axis, the rise to the right and rise to the left, or if the coefficient is negative, they will fall to the right and fall to the left. So just to see those, so an even degree, our first even degree is, they don't do it, is y is equal to x to the 0th. And there we have an even degree function. It's our first even degree. It's a constant function. It's just a horizontal line. Now let's do our next even. Y is equal to x squared. And if we call and require that the degree be greater than 0, that's our first even degreed function. Whoops. Now let's do y is equal to x to the 4th. Notice again down here it gets more narrow, and then there's a point which is at 1, 1 or minus 1, 1, in which it gets wider. Y is equal to x to the 6th. Again, that transitional point is at the point x is equal to 1, y is equal to 1, and above that point it's more narrow, below that point it's more wide. That's an interesting reason. You should think about why that is. Let's just do one more weird one. Y is equal to x to the, we did 1001, so we'll do 1002. I guess I have to make that an exponent. And again, we see the same type of squaring-like behavior. But if we zoom down really, really close and really zoom in, we see it's not a complete right angle. There is a point, if I get in close enough, that looks very much like the curve that we see in our other functions, which the even degree is not so large. So here are some basic facts. So our base function is a polynomial function. The leading coefficient is a instead of a sub n. So f of x is equal to a to x to the nth. So let's look at some facts about the graphs of f of x is equal to a times x to the nth. Remember again, a is just the leading coefficient. We always assume a is not 0 because this is a degree n polynomial, the most simplest of all degree n polynomials. And since the leading coefficient of that degree must have the leading coefficient non-zero. So when the absolute value of a is greater than 1, then just like before, then the graph of f of x is equal to a x to the n is stretched vertically. It makes it more narrow. When the absolute value of a is between 0 and 1, then the graph of a times x to the n is shrunk or compressed, making it wider. I just like more narrow and more wide. That's what does it for me visually. Now, if the graph of g of x to the n is equal to minus ax to the n, well, that's just the graph of f of x equal ax to the n reflected across the x-axis. That means that if x comma y, which is really equal to x f of x, is a point on the graph of f of x, obviously, then x minus y, which is equal to x minus f of x, is a point on the graph of g of x. So you should explore all of this so you get a good conceptual understanding. And I really think it's overkill and to plot points or to do tables of values on your own, because the whole point of this is to get a visual intuition and a conceptual understanding. If someone forces you to do all of this by literally plotting a table of values or creating tables of values, much of the learning gets lost in the computation of the tables of values. And I don't see that that should be the particular lesson here. Probably get good at computing, but again, at some point we've got to acknowledge in the real life we have computational devices that do it for us. The graph of g of x is equal to a times x to the n plus k. You should already know if k is positive, it shifts it vertically up, and if k is negative, it just moves it vertically down. And here, the graph of g of x, let's actually look at two of these examples before we go on. So I've already looked at two examples here, I think. I want to make sure you understand what it means. Geogebra. Well, at least something dirty didn't come up, right? Geogebra. So here we go. So let's look at y is equal to x cubed. So I want you to imagine what it means to be reflected across the x-axis. So if you take a crease in the paper here and you fold, I don't know, because you're going to have to do a crease right down there too. Let's just take a look and you all figure it out in your own heads. So now let's look at y is equal to minus x cubed. So actually I'm going to move it over just a bit. So what do I do to make it move to the right? I subtract some number. There we go. So here's the original and here's the reflected. I just wanted to move the reflected over just a little bit. Literally what is in the red here is not the reflection of what's in the green. It's the reflection of what's in the green that's later moved to the right 3 units. So that has, let's add one, or let's add a 10 to it, and that's going to move it up all the way up here. If I do a minus 3 instead of 10, it moves it down from where it was 3. So just the same stuff of what we're doing, except we're literally looking at higher degree polynomials. So graph each polynomial function. So you pretty much start with the graph of f of x is equal to f to the x to the 5th, and then what happens when you subtract 2 from it? You take the basic graph of f of x is equal to x to the 5th, and you move it down. So the first thing you would do would take note. Just kind of, this polynomial is a degree 5 polynomial. So you already know that its endpoint behavior is going to be different than a degree an even degree polynomial. So it's going to look like something like this. So let's just kind of sketch that in. I mean, it's not easy for me to sketch it here. That's, well, really bad. So let's just make that really big right there and pretend it goes to the origin. And of course I would need to erase this right here because it never turns back in on itself. It always continues to leave. So let's just pretend that this is y is equal to x to the 5th. It's an odd degree, and we know at the point 1 and 1, or maybe we don't. Maybe I didn't note that for you. And minus 1 and 1, there's going to be things that are different than, say, y is equal to x to the 3rd. It's going to be wider down below and more narrow up above. So when I subtract 2 from it, it's like I'm going to take the entire thing and move every point down by 2 units. So it would look something like this. There. And this is really the skill, and this point right here would be the point 0 minus 2. So let's see it done really nicely using Geogebra. Let's turn off these. So we have y is equal to x. Let's do x to the 3rd first. And then let's compare it with y is equal to x to the 5th. And let's zoom right in. So right there is what I was talking about. Right there is the point 1, 1. And right here is the point minus 1, 1. And for values of x between 0 and 1, it's wider than y is equal to x cubed. And the same over here between the points 0 and minus 1. But for values of x greater than 1, it's more narrow. And less than minus 1, it's more narrow. So let's do the shift. What was the shift? I forget what it was. Was it minus 2? Yeah, it was minus 2. So minus 2 will move it down. And that's exactly what it did do. It just simply took this entire graph here, and like if you could just lift it up, it moved it down. So here we're going to be combining an awful lot, or not maybe an awful lot, it's an exaggeration, but more than one. So I'm just going to sketch right down what I have right here. My notes for this are all over the place, so I'm not using them, and I've decided this is going to be a wholly computational visual approach using what we know. So let's actually start building up on this. The first thing about this is an odd degree function. So even though it's x minus 1 is the base, when I take x minus 1 and I cube it, I'm going to get a degree 3 polynomial. So let's build this up. So let's start out with our base function. Not that. M of x. That's going to be x cubed. And we already know what it kind of looks like. Then what are we're going to do? We're going to go n of x is going to be x minus 1 cubed. So just make sure the first observation is going to be the function is odd. Let's see if I can't write that a little bit better. I feel like I'm sitting in a wrong place with respect to my writing pad. So n of x is just a shift of m of x to the right one unit. So this is a horizontal right shift. Now we're going to do m in, I guess we'll do r of x. R of x is going to be 2 times x minus 1 cubed. So that's going to be a vertical. So my value of 2 is greater than 1 in absolute value. It's going to be a vertical narrowing. It's going to be more narrow. It's going to be more narrow than n of x. Then what I'm going to do, create another function, f of s of x is minus 2 x minus 1 cubed. Notice s of x is equal to minus r of x. So this is going to be a reflection. Reflection across the x-axis. And then the final thing I'm going to do, I'm going to call my final one f of x, and it's going to be minus 2 x minus 1 cubed plus 3. So it's just going to take the graph of s of x and move it up vertically 3 units. So let's do this in GeoGebra. We will start, I can keep here, we will start with our base function. F of x is equal to y to the x. And then we'll start another function. And we will do it, call it x. We'll let the computer name it x minus 1. And we're going to cube it. And remember, it's just going to move everything over 1 unit to the right, and that's what we just did. I don't know why it's the same color. So that was what the transformation of the original was moved over to the right. Now I think what I did was I multiplied it by 2 times x minus 1 cubed, and not cubed, not squared. And notice it's more narrow. It became more narrow. And then I did minus 2 times x minus 1 cubed. And that's our reflection. Notice that what I have in blue is the reflection across the x-axis. So make sure you understand what that reflection is. And then the final thing is I took p of x and I added 3 to it. And that just moved everything up by 3 units. So right here it kind of, there's a natural crossing at 1, 0. And here we have that crossing at 1, 3. Everything was moved up by 3. Okay, some more stuff. So the zero, this is really important. The zero of a polynomial in the variable x is a value of x such that f of x is equal to 0. So y is equal to 0. This is where the graph crosses or touches the x-axis. Intersects it in some way, either touches it and bounces back or crosses it. We have to find the value of x which makes it true. So that's different than finding the y-intercept. To find the y-intercept, I just plug in 0. So graphically, this corresponds to a place where the graph of the polynomial, just what I said, touches the x-axis and bounces back. That's one possibility, or just crosses. So here we have an odd degree polynomial. 3 examples. It crosses the graph in 1, 2, 3 places. And notice it's the graph of a degree 3 polynomial. Let's look at its factorization. 2 times x minus 1 times x plus 2 times x plus 3. So if x is equal to minus 3, this entire thing, if x is equal to minus 3, then x plus 3 is 0, and 0 times these other 3 factors is 0. So that's a 0 of the polynomial, and indeed it corresponds to x is equal to minus 3 right here. If x is equal to minus 2, then this factor, x plus 2, becomes 0, and this entire product is 0, so that corresponds to the next crossing. And if x is equal to 1, then x minus 1 is equal to 0, and the product of all 4 of these factors is 0, so that corresponds to this point right here. So when a continuous graph, and polynomial functions are always continuous, remember that means you could graph them without ever taking your pen off the paper. If it crosses a axis, if it's going to cross again, it has to turn at some point in between those 2 crossings. Keep that in mind. Here we have another odd degree polynomial. It's a degree 3 polynomial, and it only has one real 0. Notice the factorization is given to you. It factors into 3 factors, 2 of which have non-zero imaginary parts. There is minus I and I. So the only 0 it has is x is equal to 2. If x is equal to 2, then 2 minus 2 is 0, and the product of these 3 things becomes 0, and right there we see it. It only has one real 0. Now if x were equal to I, it would also be equal to 0, and if x were equal to minus I, it would also be equal to 0. But guess what? I and minus I do not appear on our graphs, because our graphs are only used to plot real valued functions. Here we have a degree 5 polynomial. Here is its factorization. Notice in its factorization, if we add together the exponents on each factor, 2 plus 3, I get 5. And if x is equal to 1, then the product of these 2 factors are 0, and it corresponds to that crossing. If x is equal to minus 2, then this factor is 0, so the entire product of 2 factors is 0, and it corresponds to that crossing of the x-axis, or polynomial 0. Now let's look at the even degrees. The same thing goes again. They're factored for you. That's really nice. This factors into 4 linear factors. So if x is equal to 1 or minus 1, 2 or minus 2, then it crosses the x-axis, and each one of those values is called a 0 of the polynomial. So let me make sure you get that in. Maybe I could write that down. I'm not using my digital board very much this time around, so but I do want to make sure you get that. So a 0 of a polynomial function because that's what we're talking about right now. It actually extends to any function, but if a polynomial function, and here it's in the variable x, in the variable x is a value of x, or it could be values, such that f of x is equal to 0. So let's look at this particular polynomial function. We were given that f of x is equal to x to the fourth minus 5x squared plus 4. And they've actually factored that for us. It becomes x minus 1, x plus 1, x minus 2, and x plus 2. And we observed that if x is equal to 1, then this first factor is 0. If x is equal to minus 1, the second factor is 0. If x is equal to 2, the third factor is 0. And if x is equal to minus 2, the fourth factor is 0. So these are the zeros. This is the set of zeros for this given polynomial. So by what I just said, that means f of 1 is equal to 0. Means f of minus 1 is equal to 0. F of 2 is equal to 0. And finally, f of minus 2 is equal to 0. Here's another last example. Notice how nice the factorization helps. Like, if I look at the first expression, it's called the expanded form expression, the only thing I can really glean is it's a degree 6 polynomial, and that the leading coefficient is negative. But when it's factored, notice that this factor has an exponent of 3, this factor has an exponent of 2, and this factor doesn't have a written exponent, so it's assumed to be 1, and 3 plus 2 plus 1 is 6, and this is a degree 6 polynomial. But from the factorization, I know completely all of the real zeros of the polynomial. If x is equal to minus 2, then this factor is 0, so the product of those factors is 0. So x is equal to minus 2 is 1 real 0. If x is equal to minus 1, then x plus 1 is equal to 0, and x plus 1 squared is equal to 0, so f of x is equal to 0. And if x is equal to 1, this factor at the very end is equal to 0, because 1 minus 1 is 0, and 0 cubed is 0, and 0 times these other two factors is 0, so f of 1 is equal to 0. So here we have, on the graph, we know, at least we know, that the polynomial is going to either touch or cross the graph right there at those 3 points. So let's do some more observation. In each of the graphs on the previous page, the number of zeros for each polynomial never exceeds the number of linear linear factors with real number roots. So what's a linear factor? This is a linear factor, this is a linear factor, this is a linear factor, this is a linear factor. X plus 2 is a linear factor, x plus 1 is a linear factor even though it's squared, and x minus 1 is a linear factor even though it's cubed. nor does the number of zeros exceed the degree of any polynomial. So if we look at this, it has 4 real zeros, and our degree of the polynomial is 4. Here we have 3 real zeros, so it doesn't exceed the degree of our polynomial, which is 6. This is a degree 3 polynomial, and it has 3 real zeros. This is degree 3 polynomial too. It only has 1 real zero, but the whole point is it's not greater than 3. And here we have a degree 5 polynomial with 2 real zeros. So it's an interesting observation that the number of real zeros never exceeds the degree of the polynomial. It can be equal to the degree of the polynomial, like we have in this case. This is a degree 3 polynomial with 3 real zeros, but it can never exceed that. The proof of that, and there's various proofs, is called the fundamental theorem of algebra. I'm pretty sure there's a fundamental theorem of arithmetic and a fundamental theorem of algebra. I'm almost certain that's the fundamental theorem of algebra. So, in order to understand the fundamental theorem of algebra, which its proof is, once you get to complex analysis, it's pretty straightforward, but we're just going to kind of give you some intuitive reasons. So a turning point is a point on the graph of a polynomial where the function changes from increasing to decreasing. So here we have the function is decreasing, decreasing, decreasing. Then it changes and starts increasing again. So that's going to be a turning point. So you can think of them as crests or troughs of a function. Here the function is increasing, 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 and it starts to decrease right there, so there's another turning point. Decreasing, 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 decreasing. There is our other turning point. So a turning point is a point on the graph of a polynomial where the function changes its behavior locally from increasing to decreasing, or of course the other way around, from decreasing to increasing. So here we have a turning point theorem. A polynomial function of degree n has at most n minus 1 turning points. Why is that? Well, if this is a 0 of a polynomial and this is a 0 of a polynomial, the only way that I can cross the x-axis and then crosses again is turn around and go back the other direction. So here I am decreasing, decreasing, I cross the x-axis, it's decreasing. The only way I can cross it again is if at some point I turn in reverse direction and start increasing again, and that point is called a turning point. And now let's talk about the end behavior. The end behavior of the graph of a polynomial is what happens to the graph as the absolute values of x get really large. Or put another way, as x gets really, really larger, going down the positive direction, or really smaller or more negative, going in the negative direction. So we talk about what happens to f of x as the values of x go to infinity. So let's do the x goes to infinity thing. So just remember that it's really important that you get the conceptualization of this right. So here's our Cartesian plane. That's where we do all of our graphing. So as x gets bigger and bigger and bigger, that means I'm traveling down this direction on the x-axis. We denote that as x goes to infinity. And when I say bigger, I mean gets really, really, really big. So the question we often ask is, what happens to y when x gets bigger? And another way to talk about that is not use y, but rather f of x. So here's a graph of a function. And if the behavior continues as it is, first, looking at this, you should suspect a degree, what? An even degree polynomial. And this is a point x, f of x. Always remember that. The x corresponds to this x, and the f of x value corresponds to that value on the y-axis. Y is really f of x in this case. So we want to know what happens to the y value as the x value gets bigger than bigger. Is it that in this case f of x also gets bigger and bigger? In which case we would say the y value, or the f of x value, goes to infinity. That won't always be the case, but this is a fundamental question. What happens to f of x as x gets bigger in the positive direction? But we also want to know what happens to f of x as x gets smaller and smaller, or I guess more and more negative, as x approaches minus infinity. So those are two interesting questions. As x approaches minus infinity, in this case, what happens to f of x? F of x gets bigger and bigger, goes to infinity. So that's me writing it down. So what happens is x goes to minus infinity. What happens to what? What happens to f of x? So this means f of x goes to an infinity, or f of x goes to minus infinity. With that said, let's look at this odd degree function. As x gets bigger and bigger and bigger, f of x goes to infinity. Here they say rises y goes to infinity, but remember y is equal to f of x. As x goes this direction to minus infinity, the function falls to the left, so y goes to minus infinity. It's another way of saying f of x goes to minus infinity. Over here again, an odd function. As x goes to minus infinity, f of x goes to positive infinity. As x goes to positive infinity, f of x goes to minus infinity, because it's going down, and this is the x-axis going, the y-axis going down this way is going to minus infinity. So here are some really good end behavior figures. The first thing we do is we look at odd degree functions, and we consider the leading coefficient. If the leading coefficient is greater than 0, then this is the endpoint behavior, which tells you as x goes to infinity, f of x goes to positive infinity. As x goes to minus infinity, f of x goes to minus infinity. On the other hand, if a, the leading coefficient, is negative, it's just the opposite. As x goes to plus infinity, f of x goes to minus infinity. As x goes to minus infinity, f of x goes to plus infinity. And down here, it's really kind of much easier in a certain sense with even degrees. So here are even degree. So here, x either as x goes to infinity or minus infinity, f of x goes to positive infinity if the leading coefficient is positive. If the leading coefficient is negative, then as x goes to either direction of the infinities, f of x goes to minus infinity. So let's use all of that to match the following graphs. So based on the discussion of the end behavior, match each function with its graph. So let's look at A. F of x is equal to x to the fourth. So this is an even degree function. So that means B and D cannot possibly be graphs of A. So it's up to graph A, capital A, or graph C. Now our leading coefficient here is 1. It's not written, but it's 1, and 1 is greater than 0. So that means as x goes to infinity, f of x goes to positive infinity. As x goes to minus infinity, f of x goes to positive infinity. You can think of it this way. When we were looking at the quadratic function and the leading coefficient was positive, it opens up. If the leading coefficient is negative, it opens down. Notice here the opening down, it kind of does some funky stuff in between, but the same is true if we look at the degree 6 polynomial. Its leading coefficient is negative, so it opens down. Opening down means as x goes to either positive or negative infinity, f of x goes to negative infinity. When the leading coefficient is positive, greater than 0, as x goes to positive or negative infinity, f of x goes to positive infinity. So we just killed A and B, because those are our even degree polynomials. So no need to graph, just match. So now let's look at our odd degree polynomials. So that's going to be B or D. Here my leading coefficient is 3. So it's greater than 0. So as x goes to infinity, f of x goes to positive infinity. If x goes to minus infinity, f of x goes to minus infinity. So the graph that corresponds to C is graph capital letter B. And of course, by the process of elimination, that means D corresponds to D. Notice again, D is an odd function. So that tells you already it's not going to have opening up or opening down, but at some point it's going to be kind of reflected across the x-axis. Not really, though, because of all this stuff right here. It's just we're looking at the leading term, and the plus x minus 4 is what does all this junk in between. So here the leading coefficient is minus. So as x goes to plus infinity, f of x goes to minus infinity. As x goes to minus infinity, f of x goes to positive infinity. So really think about it. The lecture's over and we did very little math. This is literally just mathematical reasoning. And that's an awful lot of what higher mathematics does. We don't really care what happens in this part right here. We care what happens to the function when the values get bigger and bigger and bigger. We look at the big picture and don't worry about the smaller details.